right, so I hope everyone has a beer, because the next 45 minutes is just solid mathematical derivations. You clap now, just wait. So I'm going to talk a little bit more about machine learning and kind of what we do here in the Oracle Data Cloud. But before we do that, my screen is not updating, so I'll just look up here. I kind of wanted to pose the question, since it's kind of hard to think, what is data science? And so I consider myself a data scientist, and so what do data scientists do? So to answer this question, I decided, let's mine the social web, right? Maybe that will have the answer for us. So this is my foray into mining the social web here. Data science is statistics on a Mac. All right, fair enough. Big Data Borat definitely should follow him for all your big data needs. Pressing forward, maybe that's not exactly it. Data scientist is a data analyst who lives in California. Probably true a few years ago, although now Denver's pretty cool. It's pretty hip. We have some data scientists too, so not really the right answer there. The third one, maybe you've heard a little bit more. Basically, it's just kind of saying data scientist is a little better at statistics than an engineer, and a little better at software engineering than a statistician. All right, maybe, but that kind of is putting me down in two different ways. It's saying I'm a bad statistician, saying I'm a bad engineer. So social web mining totally failed. Not going to go that route. So we're going to go a little bit different. We're going to go with the Venn diagram approach, right? And I'm sure you guys have seen this, regurgitated a million different times. Data science, you have your hacking skills, your math and stats, kind of your general expertise. This is starting to get close at it, but really, my day-to-day is a lot different than kind of combining these three skills, and especially kind of the day-to-day of my team. So I kept looking for more Venn diagrams. And I found this, and I think that this really captures what data science is, right? It's a little bit of everything all thrown together with some weird spiraling arrows around it. And so, yeah, exactly. It's unstable. So really, you look at this, and this is my first thought. Like, oh my God, what am I going to do? I got to give a talk to people and explain data science when data science is this. So I decided, all right, whatever talk I was planning, totally got to can it, got to redo this whole thing. This is my new talk title. Being lazy, the key to data science success. And so kind of what I mean by being lazy is data scientists, we have so much to do, we don't really have time to focus on everything you just saw in that other Venn diagram. And so really we need to kind of do everything at once. In order to do that, we need to be efficient, or essentially in some ways, lazy. So this kind of illustrates this as well. So Homer's here is telling his children he has three different ways to do things. The right way, the wrong way, and the max power way. And his kids ask, isn't the max power way, isn't that the wrong way? And he's like, yes, but faster. I would argue that data science is the same way. You have the right way to do problems, the wrong way, and then the data science way. And 95% of the stuff that my team puts out is totally wrong the first time they do it. Data science is a science. We're making hypotheses, and a lot of times we falsify those hypotheses. So if 95% of the stuff you're going to be doing is wrong, you better get it wrong really fast so that you get to the right thing eventually. So the way I'm going to talk about this today is kind of how can we be efficient as data scientists. And I'm going to go over the following. So I'm going to start off a little talk about architecture, and this is going to be kind of similar in nature to the talk that you just saw. Follow that up with talk about programming languages. So, right, if we're programming in different languages, there might be some that are better than others. Going to then continue talking about my team's approach to machine learning, and also just kind of a general way to approach machine learning. And then finally, we're going to close it up, since we are ODC, the Oracle Data Cloud. I want to talk about some of the work that we're doing in the Oracle Data Cloud. So, starting off with architecture here. Similar to the previous talk, I am going to argue all cloud everything. And I agree, this isn't right 100% of the time. I'm going to be a little different than the last talk. I'm going to say 95% of the time. And cloud computing can be expensive. That's usually kind of one of the big detractors I hear, but hopefully over the next few slides I can start to push you away from that idea and show you why kind of total cost of ownership might not be as expensive as you think it could be. So, kind of starting off, it's the big data meetup. And so kind of my big question is, and always my question for my own team is, do we really have big data? And how do you define big data? And I don't think there's a perfect answer, so I'm just going to go out and make my own. I'm going to say that big data is anything that you can't process on the biggest single machine that you can buy from the cloud at one time. And so, kind of looking around the net, different cloud providers, in this case, that's about almost 250 gigs of RAM, 32 CPUs. That's a ton of computing power. And, really the reason I say this is if you can get your data to work on that, I'm going to consider that small data because you don't need to necessarily use what we consider big data tools. And, it's interesting to say this, but using just plain old relational databases and sklearn is a million times better and a million times easier than using Spark and Hive. So anybody in this room who has kind of ventured out into the cluster computer, it's hard. Like cluster computer, parallel programming, all this sort of stuff is really hard. So if you don't have to do it, don't do it. Rent a big machine, use that, stick away from it. And so kind of to that extent, I'm going to talk about a case study, a real case study, although company names have been changed to protect all the innocent here. I talked to a company and they were kind of talking about this 10-node Spark cluster, which more or less I'm imagining pictured here. And the reason that I'm imagining that is, so they're telling me about this and they're like, yeah, we got 10 computers, we had them lying around, now we're repurposing for Spark, we're saving all this money, etc. I'm like, oh, awesome, and I'm thinking they have terabytes of data or whatever they're doing. And they're like, yeah, every single computer has 16 gigs of RAM on it. So do the math in your head, 10 times 16, this is the only math actually, 160 gigs, right? And so, on the last one, that's not big data. We could rent a machine with 244 gigs of RAM. They're spending all their time putting together this cluster that has 160 gigs of RAM. And so really kind of my answer to that is, that's expensive. And they're like, oh, we have the hardware already in-house, et cetera, et cetera. This is why it's expensive. First of all, clusters don't just manage themselves. You're going to need system engineers. So you need someone to keep all of this up, keep it going whenever it fails, et cetera, et cetera. Yeah, added development time. Again, it's not easy to develop in Spark, and so developing in Spark instead of sklearn, it's going to cost you some time. And that's going to be personnel. You gotta pay the people who are actually developing for you. And then also displaced work. There's so many projects that maybe your team could have been working on instead of trying to get this weird behemoth of an old Spark cluster to work. A cost of developer skill set. And so this is kind of interesting, looking at job postings, I saw a posting, not that I'm leaving, but looking at job postings, I saw a job posting the other day that was kind of asking for 5 years of Spark development. And so I assume that they're looking for one of the Berkeley students who was developing early ages of Spark. Myself, I only have a year or so, so these things haven't been around for a while. And so it's a lot easier to find someone who is a total awesome Python hacker, total awesome SQL hacker, than it is to find someone who's amazing at Spark and Hive. And so if you don't need to hire a whole team of people for Spark and Hive, or if you're hiring people that are going to learn Spark and Hive, do that, but don't necessarily try to use Spark just because you think you should have big data. And so all of these things come together, makes it expensive. And so, ultimately, coming back to my mantra for this whole talk, be lazy. It's about roughly $3 an hour to rent one of these giant machines in the cloud. Just do that, it's $3 an hour. So, the cloud is also awesome because it's disposable. And this is also going to go on my kind of lazy trend. So I have a pretty big feeling, kind of a pretty big kind of desire that my data scientists should not be system administrators. And so what I mean by the cloud is disposable is if hardware fails, you throw it away because you don't know where it is. You don't know that the hard drive just failed. You don't know that some motherboard died or something. It's in the cloud. You just turn off the computer, you turn it back on. Suddenly everything magically works again. It's great. And so I love that. And then additionally, if someone messes up your operating system, you can just trash it and get a new one. And so my data scientist team, many of them don't have computer science backgrounds. So you're taking someone with a PhD in mathematics, giving them pseudo access, and just saying, go nuts in this box. And guaranteed they're gonna probably mess it up 2 or 3 times, hopefully not a week, but they're gonna mess it up. And so the idea is, if they mess it up, that's cool. Let's just trash that machine and get a new one. And really, no support tickets, no time wasted. And so I'm not really gonna go into these tools, but there's a lot of different tools that let you just kind of set up how you want a machine to be configured. And so we use those tools. And the reason that we do is I can take kind of my entire system architecture, someone could delete, destroy all my machines. In probably 15 to 30 minutes, I could have every product I've ever made back up in the same condition. So using tools to kind of configure how you want your hardware to be and realizing that your hardware is totally disposable is the right way to kind of think about cloud computing and one of the big bonuses of using it. So data scientists should not be system administrators. Also going to go out on a limb here and say that data scientists shouldn't have to really deal with system administrators as well. No offense to any sysadmins, past or present, but really, again, kind of harping on this, science is all about experimentation. In data science, I see it as a science. And we do kind of crazy stuff. And so experimentation is all about testing boundaries. And so maybe someday someone's like, I think this code would work if we had 2 terabytes of RAM, or I think this code would work if we had a ton of CPUs, or let's try redoing everything in this way, or heavy network optimized computer. And I would say, it's so nice not to be able to have to file a support ticket, wait around for someone to kind of change the infrastructure, etc. With the cloud, you can just do that. Data scientists on your team have the power to do experimentation without having to wait. And so I think that's awesome as well. So, the cloud is scalable, and I think because of that and kind of on that, don't be afraid to throw more money, or in this case, more resources at a problem. A lot of times engineers are a little bit more expensive than your actual architecture that you're running on. And you could spend years optimizing a problem, or you could spend a very small amount of money, maybe upping your resources a little bit just to make things work a little better. And in the long term, you're probably going to save money by kind of giving that upward cost. And I think I talk here about burstable solutions. Sometimes we have solutions where we're ETLing data or something like that, and we're like, man, if I only had 500 machines for 5 hours. And so buy them, kind of pay that cost, do it, figure everything out there, and then kind of ride that out from that point on. So I guess don't be afraid to throw money at it. And later I'll give kind of a case example of how we did that, and it actually dramatically improved our time. So, I talked a lot about disposable computers, magic cloud computers. So what could be better than cloud disposable computers? Containers. And so containers are kind of a system that you can put your software in, and they're even more disposable than entire computers themselves. And so what a container has is resource isolation and allocation, just like a virtual machine, but it's a little bit more portable than a virtual machine, and it's more efficient. And so this lets your code run on any flavor of Linux, any type of box. You don't really have to worry about what the code is running on. Instead, you kind of have to worry about what the code needs. So if we containerize things, I can have a piece of software and I'm like, I want 4 gigs of memory and 2 CPUs. I don't care if it's on any certain flavor of Linux, etc. I don't care if it's being shared on 12 different computers. This is what I want. I put it in this little magical container, and somehow it gets out to a computer somewhere and runs. It's all abstracted for us. And so kind of continuing in that trend, just like the cloud, containers are even more disposable. Now you don't have to reload an operating system when someone messes something up. They mess up a container, you just kind of get rid of the container, put the same one back on, it's good as new. You can optimize your cloud usage to save cache in this way. So let's say half of my team is working on CPU-intensive processes, other half is working on memory-intensive processes. Those containers can actually coexist on the same machine because one part of my team said, I want a lot of memory. The other part of my team said, I want a lot of CPU. The container service can help to kind of figure out, oh, those guys can run at the same time. And additionally, kind of the big trend here, you can be lazy. You can change your focus of what your team's working on without having to worry about the underlying infrastructure. As a bonus, so this is Docker. Docker has a kind of container service called Swarm, and it kind of gives you some cool stuff for free. So you can set up the container service to deploy your containers in multiple availability zones. So sometimes a squirrel will chew through fiber wire and take down the whole West Coast or something like that. That sort of stuff has happened. In that case, your containers will no longer get deployed there. They'll start getting deployed to the east. So you get this kind of free location-wise tolerance. And additionally, computers, they're always failing. And so when a computer fails, the container system is smart enough to know, all right, probably shouldn't be putting code on that computer anymore. I'm going to take the containers that were running there, throw them on another box. So you kind of get that stuff for free, which is awesome. wants better than disposable containers. So my team, I put them through a lot. At first we used to be on bare hardware. Then I'm all, oh, everybody, let's move to the cloud. So we all get on the cloud. Then I'm like, oh, let's move to containers. And then they're like, all right, we got most of our stuff in containers. And I'm like, oh, now there's something even cooler. We're going to get rid of computers. And now I just seem crazy to them. But essentially, you can actually do that. And so what I'm talking about here is code as a service. So one of the new things in the cloud is running code as a service. You're not caring about architecture. All that you're saying is, I have this Python script. It wants 2 gigs of memory. I want it to run. Magic internet computers somewhere, run it for me. And this is awesome because all you have to do is focus on the code. You're not thinking about machines at all. So you get reliability for free and you get scalability for free. So that's kind of the architecture talk, and now I just want to kind of quickly talk about writing efficient software and also code. And I think it's always smart for a team not to be 100% dedicated to any language. I like to use languages and programming languages that kind of fit the need that I have. But I'm willing to change at any time. So kind of the stuff I'm going to talk about now is what I think is cool right now. 5 years from now, I'll probably tell you something totally different. If you can't tell, I changed my mind about what we're working with a lot. So I love Python. And the reason that I love Python, we can write really fast code, or we can quickly write code that's decently fast, actually. It's fast enough that a lot of our bottlenecks aren't really the code itself, and it's not really worth it for us to write C or anything low level. The code is really readable. To make fun of all the data scientists on my team as well, if, for example, I taught them all Perl, we'd probably have some horrible looking software coming out. Python makes you put whitespace in, which is actually beautiful. You can kind of read through the code easier, especially even if you don't really know how to code that well. Not that they don't, but in general, you can always get kind of better code, and people's code looks the same. And Python code can kind of fit in everywhere, and there's just a lot of support for it. I hate reinventing the wheel, so if someone's already done something, then I say, let's kind of work off that code base. So that's why I love Python. And so I'm going to give you a case study now as I kind of transition. I want to talk about big data processing. And there's been a lot of languages over the years for big data processing, so we're going to go back to this case study. This is me, circa year 2000, pretty much same sort of guy, a lot more hair. And I was working on the human genome at the time, which at the time was pretty big data, and there weren't really a lot of awesome tools to work on big data. And so I had to write parallelized code. It was a cluster that had 122 processors, which at the time was pretty cool. But I had to write code myself. And so I wrote all of the code using MPI and C++. And I don't know if any of you guys have ever coded in MPI or probably in even C++. This on the right, which you can't even read the code, is a simple MPI program. And it's not simple. It's really hard. I spent 2 years of my life writing this giant data suite that probably, thousands and thousands of lines of code. You could probably write in like 200-300 lines of code nowadays. And so really the idea here is that kind of how you're coding software, that and how you're coding parallelized software has changed. And so we should adapt to those changes. And so what do I really like? So nowadays, I'm a pretty big Spark fan, and I'm a pretty big PySpark or Scala fan. And so kind of to give you a quick example here, on the right is the Java code to do a simple word count program. Kind of extends, I think it actually ends at the very bottom, but it's a decent amount of code. On the left is the Python code to do the exact same thing. Being lazy, being efficient, I'm always going to choose the left, and that's what I want to go for nowadays, and that's what I have my team work on. So I'm really a big fan of Spark because of its simplicity, and it kind of goes against everything I already said, right? My team is all about being efficient / lazy, and maintaining a Spark cluster isn't that easy to do. And so kind of my mantra here is, can't someone else do it? So can't someone else do it for us? And this is essentially where we use Qubel in our interface. So Qubel maintains all of our Spark information. And what's awesome about that, it runs on the data that we already have in our cloud environment. So we're able to basically just say, hey Qubel, we want Spark. Here's kind of our AWS or any type of credentials that we might have. And we just kind of throw it up there and it runs. And you're like, sweet. And it handles all of the Spark and Hive like cluster scaling for us. So I might set up a Spark cluster that has 100 machines, but that doesn't mean that I want 100 machines to be running all the time. And so what's really nice about Qubel is that they'll scale it for us based upon the load. So maybe if one person on my team is running a couple small jobs, it'll run 2 or 3 machines to kind of handle that. It's all based in Yarn. And so when people start really hammering this cluster hard, Qubel goes and they find more machines for us to kind of process on and make our cluster grow. And additionally, if you are using a cloud provider that allows for like spot bidding on instances, Qubel will handle all of that for you. So they're trying to get you the cheapest machines possible. And additionally, all of their stuff works through a nice API. And so for my team, we're able to just kind of hit that API, not really worry about how Hive and Spark are kind of working, essentially, at the architecture level. It's all abstracted from us. And so for us, kind of the lazy, efficient way to do data science, Qubel, that's how they help us. So I kind of want to take a switch now and talk a little bit about machine learning, since that's actually like my biggest focus. And I'm going to just talk about kind of one little part of machine learning that's helped shape our problems, or helped shape the way that we do work. And that's the no free lunch theorem. So basically you might be kind of familiar with this in computer science. For any type of algorithm, you're going to have some awesome solution, but there's going to be some sort of data set or some case where that algorithm is not the best. And so what do we do about this, right? And so really the only way to kind of deal with this is try a whole bunch of algorithms for every single problem you get and try to figure out which one's working the best on the specific data set that you have. So explained a little simpler. So on the left here is a graph of height versus age from newborn to 10 years. You can look at that and you're like, all right, I think a line's gonna fit it well. So you fit a linear model, works sweet, awesome. You have a good model. Now you have the same sort of graph, but instead of newborn to 10 years, you have like newborn to 100. So, at some point you stop growing, you get really old, you start kind of getting a little smaller. So essentially we can do the same thing. So if we said, linear models, they always fit height and age. Let's try that. We try that, it's not that great. Really what we wanted was this kind of model. And so the problem was we picked the model before we actually evaluated the data, and that's not what we want to do. So what we want to do is apply the no free lunch theorem. And so this isn't Oracle code, this is just some stuff I put together this weekend. It's 38 lines, nothing amazing, all on GitHub. But basically it's really simple, and kind of the whole point of this isn't to say this is amazing code, you should all use this, but just that implementing things following the no free lunch sort of ideal isn't that hard. And so more or less what I'm doing here, I'm just kind of reading in some data, making a benchmark function, and then I'm just using sklearn and running a bunch of just base models on it. And the whole idea is, let's let the data tell us which model is best. And I do that and we get a bunch of results. So we can see here that using logistic regression is actually worse than if we just randomly guessed zeros and ones on our data. That happens. It doesn't happen often, but it does happen. This is the worst case for logistic regression. And so what we see in this case is gradient boosting is doing awesome. But it takes a little longer to train than a random forest. And so this is kind of the start of how I like to think about data science. And then from here, you can kind of, fix and tweak your models, maybe ensemble them, maybe play with the data, et cetera, et cetera. But the whole idea is to get away from this one model fits all solution. We're not trying to do that, we're trying to do science. We're trying to let the computers actually do experiments for us to figure out what's the best way of going about a problem. So that's my free lunch spiel. So now kind of in the closing, I just want to talk about what my team does doing machine learning on terabytes and terabytes of information here in the Oracle Data Cloud. So we have a pretty awesome internal modeling suite. It is our rapidly optimized, big observation, cross-validated, cheated there with the hyphen, object predictor. Or in short, that kind of spells out RoboCop. And I'm just going to give you a little taste, kind of just to say that, I practice what I preach. RoboCop does a ton of different stuff. This is just a taste of all the different models that we're running. We run bunches of models and variable reduction techniques on all the data that we get. Because the same way, we let the data decide what we're going to do. We don't try to preemptively think about how a problem should be solved. Computers are pretty much smarter than us in every way. So I wanted to kind of walk through our tech stack, just to give you an idea too of kind of everything I talked about today, being efficient and being lazy, and how we're actually applying that. So see, it all starts off with a REST API. But the REST API is not running on computers. It's running entirely as a code as a service. Because I don't want to maintain load balancing, etc. If I run it as code as a service, I can say when a certain REST event happens, run this little bit of code that's going to kick stuff off. That's exactly what I want. And I don't have to worry about computers. So all of kind of everything comes into our modeling using code as a service. Next, we hit a workflow engine. Didn't really talk about that today, but the nice thing about workflow engines is they can choose kind of what parts of your code has dependencies on other parts of your code and try to run stuff as parallel as possible. And you'll see that the workflow engine, all of its status information about what's running for kind of like operational reporting, it's just going to a relational database. We could have thrown it up in Hive or anything else, but again, relational databases are really good at small data. This is small data, so we put it in a relational database. Workflow engine is going to be running a lot of code for us. Most of the code is going to be Spark code, but it's kind of wrapped in Python. And for all of that, again, we don't want to worry about computers, so all of that is packed inside a container service. So all of our kind of modeling steps that we might be doing are all packed inside containers. And then within those containers are calling Kubel Hive and Kubel Spark for us as well. And additionally, we're kind of storing our metadata in a NoSQL database. And I haven't really talked about that, but kind of my whole thing as a data scientist is you never know what data is important, and if you can get data for free, get that data for free. So basically, everything that we do and everything that we run, we kind of throw that data, just raw JSON, into like a NoSQL database, just in case we need it later. So this kind of workflow for us has been really, really useful, and we can kind of scale this horizontally as much as we like. And as you can see here, it is all inside a cloud, which I also talked about heavily. So Spark, this was actually all the slides I had, and then this morning I was in the kitchen, and a bunch of DataLogix or ODC people are running up to me, and they're saying, "Oh yeah, really excited for your Spark talk this evening." And I got that from multiple people, and I was like, oh crap, I don't really talk about Spark. And so that was kind of what they were expecting, and I didn't know who else would be, so I figured, all right, I'm going to talk a little bit about Spark, because it's pretty cool, and I'm a big fanboy, so let's go with it. So I'm going to be talking about a huge internal modeling project that we're doing here at the Oracle Data Cloud. We're going to have almost 500 models, and there's a plus here because if you've ever worked with anyone in a product organization, whatever they ask for, the scope is going to increase millions of times before you're done. And so they're probably going to want 2,000 models by the time we're done with this. Same with number of features. That's a very exact number for this, but probably we're going to get more data, we're going to get different data sources, that number is going to grow as well. And then the number of observations. So this I would actually consider a small data set in comparison to some of the stuff what we look at with like 3 billion rows. This is only 450 million, but we have to run a lot of these models with a lot of features, a lot of observations. And of course, going back to the product org, how often do you want this thing to run? As much as possible. All right, cool. So this is what we have to work with. So we decided to use Spark for this, but this wasn't the initial solution. So actually when I joined here 2 years ago, we already had a solution. And it was pure data science at the command line. So you guys might be aware of the Born Again shell, great programming language. That all the code was written in Bash, and all of it was running Hive queries. And that's it. No machine learning libraries, nothing. Bash and SQL. All right. So we have data. That data gets modeled individually for every model. We repeat. We do that 468 times. That takes about a week to run, uses a ton of computer resources. So this is kind of my example. Sometimes you have to throw money at a problem, but the last thing here is what matters. It generates a ton of revenue. So it doesn't matter that this wasn't like the ideal situation and the ideal way to kind of implement it. It makes more money than it costs, and it works. So cool, let's run it. So that's existed for a long time. And so I came and looked at it and wanted to throw kind of my favorite tool, Spark, at it. And so I said, let's go all Spark. Keeping the same sort of workflow, data gets modeled in Spark, not in Hive, and then repeat, right? So this should be a lot faster, whatever. Still takes forever to run. Really, Bash and Hive were beating what I was doing in Spark, or roughly about the same. So Spark isn't magic. You can't just wave the Spark wand and everything works. So we had to think about kind of how we were working with our data as well. So we kind of took a step back, and this is the way that we were working with our data. So we have all the data stored in a distributed kind of Hadoop-like system, and then we're running these individual models, and every model needs a different piece of data. And so what we were doing is we'd run a model, we'd grab data from Hadoop, throw it into Spark, run that model, get the result, awesome, cool, save that result. Then we empty Spark memory, and then run 2, we go back and we're like, oh, what data does this run need? We grab it from the data store, run it in Spark, empty it again, et cetera, and so on, for 468 times. And this is why things weren't really faster. We were kind of not optimizing what Spark should be used for. So this is an example, if you have been following along with my talk, the way that we decided to solve this is throw a little bit of money at it. And so what we're throwing money at is we have all of this data and we're just kind of pulling chunks of it into memory at a time. Wouldn't it be awesome if we could just always have the data in memory? But in order to do that, you got to throw a little bit of money at it, got to get some more computers just to have some more memory. Because the cool thing about Spark is you can just scale it up in terms of number of machines, and essentially you're scaling up the amount of memory that you have. So this is the way that we kind of switch the process over. We do one data pull, and that data pull goes to a ton of machines. And it's pulling all of the data in Hadoop into Spark. And so then we cache all of that data. So now we have our entire data set, which is a ton of data, but it's all cached inside Spark. And by doing this, we found that the data pull, getting things from a physical disk across network into computers, is actually what was taking us most of the time. It wasn't really the modeling itself. And so by doing this, and just kind of changing the process this way, we took a 1-week process and basically with roughly just a little bit more computer power, turned it into only taking 11 hours. And what's cool about this, we're using a lot more computers, which cost a lot more, but they only cost a lot more for 11 hours. They don't cost a lot more for an entire week. So ultimately, even though we're kind of using more resources, it ends up being less expensive in the long run. But we weren't really done. We could have been done, but one member of my team is always trying to optimize things even a little bit more than they can be. And so he noticed really the slowest part now is distributed shuffles. So we had a lot of data on a lot of different machines, and there was a lot of shuffling between machines trying to kind of move data around for specific models, because not every model needs the same data. And so we saw this data movement. And so this kind of goes back to my idea of sometimes you don't always have big data. So some of our models are what I would consider big data. They can't be run on one machine. We run them with this kind of paradigm. Some of them are what I would actually consider a little more small data. So we kind of went back. So we have all this data kind of cached in Spark. And we went back and thought, all right, it's all cached in Spark, but there's actually physical computers that it's getting cached on. And the talking between these computers is what's spending us a lot of time. And so what this team member of mine did, he decided that we're not partitioning data the best way possible. And so the way that we had kind of data set up was every computer had different chunks of data for every single model that we were going to run. And it turns out some computers could actually hold small enough data that they could run the entire model without talking to anyone else. And so we kind of wrote a system that helps figure out how to partition data to the right computers in the right way. And for models that can just work that way, and this is all just running local Python at this point. We're using Spark to distribute and partition the data, but then we're just running Python on kind of the individual nodes. There's a huge partitioning cost to this, and that's a whole kind of data science exploration in itself. But for this kind of small data, it's super, super fast. And so really we have kind of two solutions here. One which distributes data large, and we kind of have to deal with shuffles, and one which kind of figures out efficient ways to move the data around so that we don't have to shuffle and we can model really fast. And different business use cases can occur that both of those are useful. So I did not share all of the source code of everything we wrote. I don't think I'd be fired if I did that. But people come to me a lot and they'll say, so what's the secret sauce to modeling? What makes you awesome? And I think a lot of it could be boiled down to just kind of simple rules. So simplicity in design, we try to think about everything very modularly. We try not to kind of over-focus on kind of preconceived notions and let machines do the work. Unified data storage, a lot of work is often just ETLing data, and so one of the biggest things on my team is try to get data all in the same sort of format so that anything we run will work on all data sources. And again, I talked about this, but code modularity, just trying to keep your code not all dependent on itself, trying to keep it able to be run separately. Again, as I kind of talked about earlier, no free lunch. Let the data tell you the story, let the data pick the modeling. Scalable infrastructure, so this is kind of cloud and containers and no cloud or containers, but running code somehow magically on computers on the internet, kind of using that sort of information. And then ultimately, again, data science is a science, and so for a team to be successful, we really need to experiment, and we need to do stuff. Sometimes it's going to be right, sometimes it's going to be wrong. And the whole kind of point of everything today is let's do that as fast as possible. And so kind of before I close out, a big shout out to my awesome team, all pictured here. And additionally, a shout out to the rest of the Oracle Cloud, Oracle Data Cloud. We all work together. We don't really work in isolation, despite how I say we don't want to work with system administrators. There are many times that we need to contact the system administrators to help us out. We still break things. And the big hiring pitch, my team's hiring, other teams are hiring. There's a lot of hiring going on right now, so definitely get in contact with me or someone else if you're interested in that. And with that, I will open the floor to questions. Silence.
Oh, hey, just a quick question here. Is someone asking over there? No.
No.
Okay. So you're using all these different models. You get some data set. You throw out a bunch of models. I guess it's kind of a two-part question. One is, how do you do your feature engineering kind of upfront of model selection, or do you kind of have a loop with that?
Yeah.
And second part is, are you using a holdout set because you could overfit just in your model selection process?
100%. So kind of tackling the second question first, holdout, you have to be afraid of overfitting. There's a lot of models, you can throw a lot of parameters at them, and you're like, wow, this model with 1,000,000 degrees of freedom always fits stuff perfect, and then you apply it and it doesn't work. So holdouts are always essential. And then you also bring up a good point. So, you know, in an ideal world, we would exhaust computer resources and throw kind of everything we have at every single problem. In the real world, this is why data scientists actually have to know some math and kind of some statistics behind it. Not every problem can be approached by just kind of throwing every model at it, so you need some sort of intuition. So usually what we try to do is pick a set of models that we think for reasons about the data or kind of reasons that we've run stuff in the past have been successful, and then we kind of experiment within that set. And obviously it matters upon the problem that you're working on. Some problems you might not care a lot about accuracy, you care a lot about speed, so you have to make some preconceived notations about like, all right, we're just gonna run this model because we've seen it work well in 99 other cases, let's just let it go.
How do you go about getting, say, like a new data scientist onboarded and up to speed on, you know, the sort of distributed cloud environment where you can say, okay, you can use your IPython notebook or Zeppelin or whatever, and here's your sandbox environment where you don't have to worry about screwing anything up. I take it they're not on their own to set up their own container and stuff like that. So what do you do to get them sort of onboarded and up to speed?
Totally, great question. I'm still constantly trying to figure that out as well. You know, I think the best is baby steps, and I'm a big proponent of here's a project that's 95% of the way completed, and you're kind of just, here's the code for it, you're just kind of changing a couple variables. Starting there, getting familiar with the code stack, getting familiar with what you're not familiar with. And on my team, so we try not to have very kind of compartmentalized work. Everybody kind of knows a little bit about everything. So really, it's slowly just kind of being led by example. And it is hard, and it does take a lot of work. It kind of takes like a lot of peer kind of pairing, but I found it to be successful so far.
You talked a fair bit about trying a bunch of models. I was curious how much research Oracle is doing on efficiently running a whole bunch of models and hyperparameters, because there's a lot of ML research right now for that.
Yeah, totally. So, I mean, it's bad enough to run like 20 different models, and then it's even worse to try to do a grid search of some sort and figure out what parameters are the best for them. And so that's not my group, but actually there is an Oracle Labs group, similar to labs groups you might see at other companies. And we work really closely with them on problems just like that. So the nice thing about that is they're kind of a think tank. They can go off, work on problems that aren't necessarily directly revenue generating, think up awesome solutions, and then we can try to implement those solutions working alongside them.
How do you communicate to business users or whoever your ultimate customer is what you've learned in this 468 models and why you picked this one versus that one and what they should do?
Yeah, it's really hard, right? So in the realm of linear models, you can say, oh, these are the variables with the biggest coefficient. And now when you have a random forest, a gradient boosted tree, a linear model, logistic regression, they're all put together by a generalized additive model, and you have this thing pop out, and you're like, you ran PCA on the data, you don't know what's going on anymore. And so, one thing that we try to do here is take audiences. So everything that we deal in is trying to think about audiences. And we have raw data behind those audiences. So we try to take kind of these complex modeling outputs and make them consumable for the client by looking at kind of audience distribution and composition. So we let a computer make this audience, and it might turn out that the computer finds out the audience trends to be female 25 to 30. So those are the kind of things that we would tell a client. And the modeling in between, a lot of it is trust us, it's better. And we can show accuracy numbers. We do A/B tests, we'll do live tests, we have past data, we can run stuff historically and see if this model would have done better than others. But a lot of it, it's always that hard level of trying to take very complex processes and explain them to a client. And I think we're constantly working on it.
So back to the no free lunch, how often does your model change as your data starts growing?
Yeah, it's interesting. I would say for specific use cases, models tend to be pretty stable. But I would say new use cases is usually when we find that a different model is the better one. And so for stable use cases too, sometimes it's nice to kind of hold a model in stone because you know how it performed in the past. That's probably going to give you similar performance in the future. Going again to the client idea, it might not, from my point of view, I'm like, we should always be evolving models. Clients sometimes like to know that their performance on their product is going to be the same year in, year out. So sometimes we kind of nail those models in. It really depends on us. We get a lot of new data sources all the time. And so when we get a huge amount of new data, that's when kind of the new modeling approaches might actually be more useful. And often kind of too, going back to all the questions in general, is it's not necessarily, we don't just say, oh, this model's winning now, cool, like let's just run that. A lot of times we kind of put the mathematics thought into it. Why is this model doing better? What's unique about this new data that lets model X do better than model Y? And that kind of gives us further insight into just kind of how we're approaching problems in general.
Couple of multi-part questions.
Sure.
First one on the logical model in terms of, you talked about MPI, things like that, right? So when you're dealing with clustering or distributed processing, parallel programming, whatever, there are certain issues that have to be dealt with, right? So as you create a parallel model, you have to deal with things like barrier synchronization, consistency, what happens when you have a failure, et cetera, right?
Yep.
So one of the challenges always is you can't take an arbitrary code and automatically parallelize it, right? There has to be some infrastructure that supports that.
Exactly, and I think that touches on a lot of what I love about Spark is that, when you deal with MPI, you have like, deadlocks and mutexes and all this crazy stuff going on. And Spark kind of abstracts a big portion of that away. Spark also has the idea of redundancy baked in. So nodes are failing, etc. You can kind of get away with it for free. That said, I think true parallel programming will never die. But for data science projects and for a lot of the programs that we work on, we really don't need those really complex kind of parallel programming sort of ideas that you might need if you were writing like a networking app, for example. And so we don't have to worry about a lot of those kind of more difficult things.
So I'm not trying to support MPI.
Oh, no, yeah. No, but totally,
But the
I think
point
it is
is
important, yeah.
That underneath, so you could have a messaging model, et cetera, right? So I think that comes back to your programming model. You have to be aware, at minimum, you're doing multi-threading, stateless type of things.
Mhm.
So I can sort of see that, and it's learnable.
Yeah.
The second part is the physical infrastructure. So both talks abstracted the infrastructure into a black box. But there are certain characteristics that you have to be aware of. What's the network bandwidth, latency, et cetera?
Yep.
And how do you scale? The object store, how do you scale that? So in order to make a certain set of assumptions, you have to be able to prescribe the nature of the infrastructure underneath. So how do you deal with that?
Yeah, so we actually had to deal with that. For a while, we were using, again, throw money at it. We were using a lot of kind of weaker machines with the idea that, these machines, if one of them goes down for whatever reason, it's not going to cost us as much money. If we kind of, let's say we were getting charged by the hour or something like that, if we go to an hour and a minute, they're tinier machines, maybe it's not going to matter as much on some of them. But we were kind of ignoring the network cost. And you have 1,000 machines, you have 1,000 machines all talking to each other. And so by actually spending more money on less machines that are more powerful, we were able to kind of keep more data living inside kind of CPU world and living inside memory world and getting out of this whole network world, disk world, and did a lot better. So I think that's a really good point, is when you move to the cloud, especially from going to a data infrastructure that you know about, in your server room, you can say, oh, computer A is right next to computer B on the rack, and they're connected. In the cloud, computer A could be, in a different building than computer B, and that ends up mattering at some point. And so I think it is really interesting to pay attention to that, but I think kind of beyond the scope of today.
Yeah, and just to highlight that point, because that drives the infrastructure issue. Almost all data systems, especially like Hadoop, et cetera, treat the data world as a flat topology, right? Cluster as a flat topology. The reality is you have a hierarchy of switches, inter-switch links, which will affect your performance and behavior very significantly, because almost all parallel jobs are limited by the last responding node.
Yep.
Right. So.
Yeah, no, I mean, it's definitely a topic worth time to think about as well. So, I mean, in that sense, cloud doesn't 100% save and fix everything, but kind of being knowledgeable of topics like that, you can usually work around it or figure out solutions. And that's why I said too, 95% of the time, cloud works great. There are certain use cases, high network constraints, things like that, where it might not be the right solution. Yeah, go for it.
Okay. There it is. Just a question. I'm a grad student trying to get into this world, and kind of what you were alluding to with 5 years of Spark programming experience before you can start the job, that kind of thing. I'm wondering when it comes time to hire somebody, to bring somebody onto your team. A lot of the universities are still catching up to big data. They're not teaching it in their classrooms, that kind of thing. And a lot of the students are coming out, at least my experience has been to graduate with a lot of tangential skills around the ecosystem without specific ecosystem skills. So when it comes to hiring time, what skills are you looking for in somebody to join your team? What is important to you, or how does a guy like me begin to enter into this world, which has a lot of barriers to entry on the learning side? Because I just can't go access a big data system one day just for kicks and throw it up at my house and start playing.
Sure. And so going back to this slide, when I hire, I am looking for all of these things.
Oh, okay. Yeah.
So nice and easy. But not individually, or not one person to have all of these. I try to hire around to my weaknesses. So if I notice my team, for example, is kind of doing bad in some of the big high-level system architecture, some of the problems that we were talking about here, I might hire someone who has old like C++ or like low-level programming knowledge, because those kind of people understand how memory works, how CPUs work, and they can think about how networks work. But someone coming up in this world, I think, you know, there's so much and there's so much changing out there. Both Amazon and Google will give you cloud for free. So as long as you give them your credit card and you don't go over their max usage, they are willing to give you a good amount of resources for free. There's a lot of really awesome open data sets out there. Some of them are pretty cool, like Chicago crime data I've done some fun stuff on. I would say grab one of those data sets, sign up for a free account. If the free account runs out, maybe change your name, sign up for another free account. And I was once a grad student too, I'm a very hungry grad student. You know, we don't make a lot of cash. And so I would kind of start there. Competitions like Kaggle are awesome. If someone can come and interview with me and show me how they did something in Kaggle, I'm not looking for someone who's just like, I process petabytes of data and I'm awesome. I'm looking for someone who's creative and kind of understands the infrastructure and does cool work inside it. Thank you.
Quick follow on to that. What are the shortcomings on your team right now?
Yeah, so in all honesty, my team right now is looking for the little bit more engineering focused data scientists. So that's kind of what we're hiring for right now.
Just looking at that slide there are various circles and ellipses and everything on there. Those would change depending on what you were looking to output. Like if there was another circle to the right that says, here's where whatever comes out of this montage goes to, that's going to change that quite a bit, isn't it?
Yeah, so this is actually a 3D graph where the z-axis is the project that we're working on. Try not to display that there. Everyone would need an Oculus or something like that, but you're 100% right.
How much is your team involved in knowing or identifying what questions to ask, or is that product management?
The cool thing about Oracle Data Cloud is product management helps drive products, but we really get to ask a lot of questions about, is this product the right product? Could this product be better? And we also generate kind of product ideas internally. And so how have we evolved in that sense? I think a lot of it is just like gathering war stories. We've all tried stuff, we've all had the best intuitions and seen them go wrong. And so we just kind of understand the landscape a little bit better. And just in general, as the team experiences more and more, again, data science, all this stuff's very, very new. We've just been learning more and more. We try not to repeat the same mistakes we've made in the past.
Are you guys doing anything with unit testing, specifically with your Python and Spark, and can you describe that?
Yeah. Data science is a really weird world in terms of testing. Coming from like strict engineering, test-based development is awesome. And the problem with data science, as I said again, is a lot of it is experimentation. And we don't really know the product that we're programming when we sit down at the computer. And the whole idea for my team is, let's prototype something fast. So prototyping doesn't usually include a lot of testing. As we move stuff towards production, that's where we start adding a lot more testing. I would say for my team, we don't necessarily do a strict kind of unit test-based development. We're more focused in large integration tests because also with a lot of data science is there's a lot of random elements. There's a lot of things going on in kind of complex systems that sometimes you can have a whole suite of unit tests and they're not going to capture that your model is not working. And so really we kind of lean heavily on integration tests. If someone breaks something in my code or their code, I make them make a unit test for that. That's kind of like, all right, make a unit test so we never have this problem again. So we kind of have an adaptive form of testing. Is it ideal? I don't know, but it's worked so far for us.
So is your team building low-level algorithms, or are you taking advantage of statistics packages and your focus is taking existed, tested statistical methodologies or machine learning methodologies and throwing it at your data in unique combinations?
95% of what we do, I would say, is that. There's certain cases where...
The second one?
The second one, where we are kind of taking pre-built solutions and either tweaking them slightly to our use case, or basically just kind of running them and ensembling them in unique ways. I mean, people spend their entire PhDs improving machine learning projects, and so that's not really our focus. That said, if certain data presents itself in an interesting way, we might make a take on random forest to kind of adopt that or kind of hack at the code a little bit. And again, Oracle Labs is really good at kind of making novel machine learning sort of ideas. All of that changes when you get to the world of neural networks, because you don't really throw a neural network. You're not just like, hey, network, here's some data. Neural networks you're almost kind of programming novel solutions at the same time. So that changes everything up a little bit.
Alex, we have time for one last question.
All right.
For the supervised algorithms, how do you go about acquiring training data, or really the classifications, making sure they are representative of that, the data at scale, and sort of QCing the classifications themselves?
Totally. So we are the Oracle Data Cloud, so we have a ton of data. And what's really cool about that is we have a lot of historic data. So if we're doing marketing for, let's say, a consumer packaged good product, so hot dogs or something like that, we have years and years of data about how hot dogs are being sold. And so we can go back and we can make a model in 2013 and then say, all right, we made this model in June of 2013, let's see how it would have done the next month. And we can kind of do that at multiple points back in time. So we just have so much data. We can do holdouts on that, and we can look for seasonality in data. We can look at, what happens if we combine multiple years? What if we can map trends from other data? And so really with us, we're kind of in a unique situation where we have so much data and millions to billions of rows that we can make a holdout that's still 20, 30 million rows and work our stuff on that. And so that gets to a whole another idea of how do we evaluate models, and that's also another whole thing, right? With modeling, especially like a sort of classification model, you get your confusion matrix. And you could look at that as an ROC curve, you could look at that as precision recall, you could do all other sorts of stuff, just look at accuracy. And ideally what we do is we look at everything we possibly can. And we try to look at that and just say, is this in every weird three-dimensional way that you can look at it the right way to go about solving this problem? Cool. All right then, so I think socializing time, beer. Let's do it.